welcome back to my favorite people. In this lecture, I'm going to go through substitution reaction, and the one that I will zoom on it will be the concerted mechanism. And we call it SN2. S stands for substitution, N for nucleophilic, and 2 means you have molecularity equal to 2, or 2 particles are involved inside the rate determining step. Okay, and the first particle, it will be the nucleophile, and the second one, it will be the substrate. The nucleophile will share 2 electrons with carbon. Carbon, it has a partial positive charge, and when it gets those 2 electrons from nucleophile, very soon it will let those 2 electrons to be taken by the leaving group or the halide, and the leaving group will get those 2 electrons and to leave the system. When it's leaving, it's going to leave with the lone pair, so that means it's going to be acted, and the formal charge for it might be, might be 0 or -1, might be 0 or -1. Okay, the attack must happen from back of the system. As you see, we have here we have nodes. So when the nucleophile is reaching, if it can make it, let's say constructive interference, or like an interaction with the positive positive lobe, the negative one, it will cancel it. So the interaction is not going to be effective if the nucleophile reach it from this position. But if you reach it from the back of the molecule, you have one lobe, and that lobe, whether it's negative or positive, any sign that you give it to it, and the interaction, it will be constructive, and it will be strong enough to kick the halide out of the system. So the attack must happen from back of the system. And while the nucleophile is coming and getting inserted to carbon, the halide at the same time is leaving the system. And all this happening in one step. So that's the reason we call it concerted mechanism. Okay. So addition of the nucleophile will happen from back of the leaving group. This is going to be our leaving group. Okay. This is going to be the leaving group, and it is involved in the sigma bond with carbon. So this is going to be our sigma bond. Okay. So that's going to be the sigma bond. And what do I have here? I have a lobe. Okay. That lobe, okay, any sigma bond, if you remember, say, if you have, for example, a carbon here, and that carbon involved in a sigma bond, it will have a tiny lobe there, and that lobe, it will be technically we can say that's going to be the sigma star. Okay, sigma star orbital. So the sigma star orbital is back of the molecule. Okay, back, and we can reach it from the back. And if you reach the molecule from the back and make interaction, and that for sure is going to change the configuration of the stereocenter. If you have a stereocenter, the configuration, it will turn to opposite thing. So keep this one in your mind. In SN2, our configuration, it will turn to S, and S, it will turn to R. Okay. So if you start with R, you get S. If you start with S, you get R. Always respect this. Okay. And okay, let's talk about it. Why this one is happening, and what do we have? What's the mechanism? So this reaction is gonna be, let's say, SN2. So I go SN2. That means you have a reactant that is reacting with a nucleophile. So here I'm gonna say I have a reaction coordinate. So I go reaction coordinate. Then I go say delta H, or energy of the reaction, energy of the system. So you can just simply call it energy. Okay, just simply call it energy. So let's call it, okay, energy. Okay, I have a reactant, and let's say this one is our reactant, and reactant. Okay, product, I'm gonna put them here, and now I will connect these two. Okay, gap between reactant and product. I will call it delta H of the reaction. So this one will be the product, and that one is the reactant. And gap between the maximum point and the horizontal line, we're gonna call it activation energy. So this one, it will be the EA, and the max point, we call it transition state. Okay. I want to draw the geometry of the transition state. Okay, this is going to be the geometry of the transition state. So you have, okay, you have this reaction. Okay, and so inside the transition state, carbon, it will be completely planar. Okay, that means we're going to have hydrogen facing to us, while the methyl is back of the molecule, so this is going to be methyl, and ethyl, it will be down and but inside the plane. Okay, and this one, it will be the ethyl, and that's going to be, we said, the hydrogen. Okay, where is the bromide? Bromide is here. Let's show the bromide. Bromide, I'm going to show it by, okay, dash line. And so that's going to be the bromide. Bromide, it will be the leaving group. So bromide is going to be the leaving group. And our nucleophile, it will be the SH. So SH is going to be the nucleophile. SH is coming in this direction. And remember that these three are forming a plane. So they are in one plane. And that plane, it will be completely flat. And the bond angle between the groups, it will be 120. Okay, so geometry of the transition state, okay, geometry, it will be trigonal bipyramidal. Okay, trigonal bipyramidal. You can assume it like that. You have a carbon, two groups that are attached to it, and one group is the nucleophile, SH. Okay, SH is trying to come to the system, while bromide is leaving the system. And then what do I have here? I have three groups there. And I have, let's say, hydrogen, say methyl, and we have the ethyl, for example. Okay, those are forming a plane for me. And the bromide and SH cross off each other. I want to say this: the bond angle between those, the incoming nucleophile and the leaving group, bond angle is 180 degrees. When you insert the nucleophile to the carbon, and that's going to kick the halide out of the system or the leaving group, and also will change the the configuration of the stereo center. Okay, and it will turn it from whatever it is to opposite. For now, okay, I have 1, 2, 3. This is gonna be R, but because hydrogen is facing to me, it will be S. Okay, so the starting configuration is S. And what's going to be the configuration of the product? And the configuration of the product will be this one. Okay, so I started with S configuration, and the product, just simply, okay, add the SH from opposite side. Okay, so you add the SH from opposite side, and right now it's inside the plane. Next, you have a carbon. Keep hydrogen facing to you. Hydrogen is facing to us. Where is the methyl? Back of the molecule. This is the methyl. Where is the ethyl? Is inside the plane. And this one, it will be the ethyl. Okay, let's now figure the configuration. And here, the configuration, I have this one is 1, this one is 2, and that one is 3. So rotation is telling me this one is supposed to be counterclockwise, S, but because hydrogen is facing to me, it will be R. So I started with S configuration, but I got R configuration at the end. So this is going to be an SN2 nucleophilic, so nucleophilic substitution, and then the order is 2. Okay. Rate of the reaction is subject to concentration of SH, the nucleophile, and also subject to concentration of the substrate. Okay. So rate is subject to both of them. And I'm going to say this, rate of the reaction is equal to K multiply, okay, the substrate, or the alkyl halide, multiply the nucleophile, concentration of the nucleophile. Sorry. And from each, I have 1, 1. So this reaction is a second order reaction. Okay. And because it's a second order reaction, if you double concentration of, for example, if you double concentration of the nucleophile, then the rate will be 2 times faster. Okay. And they might ask you, because this one is a second order, what's the unit for K? Okay, how do I find unit of K? Say this, the unit for K, it will be M1 minus N multiply S minus 1. And what's the N? N is order of the reaction. So it will be M1 minus 2 multiply S minus 1. Reaction here, the unit for K, it will be minus 1 to S minus 1, which is equal to 1 over M multiply S. This is a second order reaction, and K is the rate constant, and unit for the rate constant is 1 over molar to second. Okay, so we know reaction is concentrated. What does it mean? It means entire of this reaction is happening in one step. You have only one activation energy, and that activation energy is subject to concentration of the nucleophile and the substrate, and at the same time. Okay. There are some factors that we need to study them, and they might affect technically the rate or fate of the reaction. And one of them is going to be the steric effect, the second nucleophilicity, the third one will be solvent, and the fourth one is going to be temperature. A temperature, it will be very critical when you have elimination versus nucleophilic substitution. And but let's start with the steric effect. Still, we are talking about the substitution, and I want to know what's the effect of an steric effect on the SN2 reaction. Okay, so remember, in order to kick the halide out or the living group out of the system, we need to reach the molecule from the back. And in order to reach it from the back, we need to have technically a free space to reach it. And if your halide or living group is sitting on carbon with less substituent, less steric effect on it, it will be easier for the nucleophile to reach it. And so if it's a methyl, because you have 3 hydrogens sitting on carbon, and those 3 hydrogens are not going to create huge steric effect, reaching carbon, it will be way easier. And because it's easier reaction, it will be faster. Okay, but if you replace like one of the hydrogen by methyl, okay, so still I have 2 hydrogens, and now I got methyl. Reaction, it will be slower, but still it's fast enough. And as you move to tertiary, reaction get slower and slower. And in fact, the tertiary will not much be involved in SN2 reaction. It will try to run the reaction through a different mechanism. So steric effect, as you increase the steric effect, you will reduce reactivity of the reaction toward technically SN2, okay, SN2 pathway. And so what's the best substrate, okay? Best substrate for SN2 reaction, the substrate with less groups attached to it, either a primary or a methyl. Okay, primary and methyl are the best, the best technically substrate for SN2 reaction. Okay, and why the rate of the reaction it will be slower if I increase the groups? Okay, look, your nucleophile is supposed to reach the alpha carbon. This is the alpha carbon. As you increase the group around carbon, reaching carbon, it will be harder. And for now, I'm going to replace one of the hydrogen by methyl. Next time, I will replace two of them by methyl. So as you see, methyls are bulkier than hydrogen. Because they are bulkier, that will make it harder for the nucleophile to make it to the alpha carbon. And that's the alpha carbon. Because reaching the alpha carbon gets harder as we increase the substituent on the alpha carbon. Okay, the reaction will be slower. Okay, reaction will be slower. How? Because the activation energy is going to go up. So as you see, by replacing, hydrogen with methyl, the activation energy went up. And when is a secondary carbon, the activation energy is way higher than primary. And this is the order for SN2 reactions. If you have methyl halide, methyl iodide, it will be the fastest SN2 reaction. Now, if you replace one of the hydrogens, okay, if you replace one of the hydrogen by methyl, reaction will be slower. Okay, that's it. Primary, yes, that's a primary. We had the methyl, now primary. Okay, next, this is a secondary. It has two methyls and of course one hydrogen. And how about this? This one still is a secondary, but the difference between them, on the beta, one of the beta, I have substituent. Okay, so that means if you increase the steric effect on the beta carbon, not just the alpha carbon by itself, you're gonna reduce the speed of the reaction. Okay, so maybe it's not that significant as increasing this group on alpha, but still you are increasing. So you're increasing the steric effect, and that's gonna slow the reaction. So as you see, between these two, both of them are secondary, but here we have CH3, while that one replaced by methyl groups. So it's going to be bulkier. And then I have tertiary. And the last one is a phenyl, okay, phenyl ring. In fact, the phenyl ring is not going to get involved in SN2 reaction. So here, say no SN2 reaction. Why? Because you have carbon with sp2 reaction, sp2 hybridization. Okay, so phenyl is not really going to go through SN2. Why? Because you have carbon with sp2 hybridization, and that one is going to be a really weak living group, and so it's not going to happen. And we will review that one. Okay, here I put some data to compare primary the steric effect on alpha versus the beta carbon. And if you treat this one as a reference, when you change okay, one of this hydrogen to a methyl, okay, and you see the reaction, it will drop down by 140 times. 140 times it will be slower. Or if you replace hydrogen, the methyl group by hydrogen, so if you replace this one by hydrogen, you see the reaction is going to be 145 faster. Okay, one methyl changed rate of the reaction by 145. Okay, now if you have two groups, two methyls on alpha, the reaction is going to be way slower. And if you turn it to a tertiary reaction, in fact, it's not going to go through SN2. Okay, this one is not going to happen. But how about the beta? Beta, the difference is not that much, and this is the proof for it. And if we treat this one as a reference, and when we change the methyl to hydrogen, if we change this methyl to hydrogen, reaction it will be faster by 0.2, so it's not that significant. Well, here when we changed it was 145 faster. So I'm going to say the steric effect is more important on the alpha carbon, not the beta. But it doesn't mean beta is not significant. You have to include it in your calculation. And thank you very much.